Hi guys, today I would like to present about smart instrumentation for vehicle emission monitoring for analysis and proposal of multi-gas sensor system for automotive sustainability. So as you can see, these are our group members, which is Rizwan, Hakim and Alif. Let's start with the first slide, which is a problem identification, which is urban air pollution. The challenge rapid urbanization has led to massive increase in vehicular traffic, releasing the toxic gas into urban ecosystem. First, release a critical concentration of NOx, NCO, and particulate matter PM. 2. Highly regulated with observed count levels, ozone, and hazardous acid rain. 3. Direct catalysis for increased respiratory illness in the diesel populated zones. And last, significant contributing drive of the global greenhouse effect. For the next slide is inflation monitoring. Why problem persists? Legacy measurements models suffer from several physical and temporal constraints. Understand operations like first, sensor degradation is exhaust sensor drift over time, feeding incorrect compositions data to the vehicle ECU. Second, delay detections, faulty or incomplete completions remain unnoticed until serious engine issue arise. And lastly, there is complete data, which is a conventional setup like selective gas sensing limits required for modern Euro 6 standard compliance.
Moving into our proposed solution, I would like to introduce to our smart multi-gas zirconia monitoring system. This architecture is built around 3 core hardware components designed to withstand harsh automotive environments while delivering high-speed data. First, we have the sensing probe, which is positioned directly inside the high-stress exhaust manifold. It is engineered to track raw gas concentration under massive thermal and physical pressure. Second, the probe feeds raw data into the control module. This module acts as the brain, converting low-voltage electrochemical data stream into filtered, clean, and high-resolution signal. Finally, we utilize a CAN bus interface to establish rapid real-time high-speed communication lines directly with the vehicle's central engines control unit (ECU). Together, this component create an active dual feedback loop. This allows the vehicle to dynamically regulate air-fuel ratios and optimize urea injection protocols for selective catalytic reduction (SCR) system in real time. Now, let's dive into how this sensor actually works on a chemical and physical level. The foundational mechanism relies on a heavy-duty zirconium dioxide (ZrO2) ceramic electrolyte. Under normal temperature, this ceramic is non-conductive. However, once it is heat past 300 degrees Celsius, it is crystal lattice shift and is transitioned into a highly active oxygen ion conductor. As you can see in the diagram, oxygen vacancy allows ions to migrate across the material. To calculate the actual concentration of oxygen, the system utilizes the Nernst equation. By comparing the constant oxygen pressure, our reference ambient air, which sits at 20.9% against the changing exhaust sample pressure, a distinct voltage potential E is generated across the inner and outer platinum electrolytes. The inner and outer platinum electrodes. This voltage is read by DC voltmeter and sent to our control module to determine the exact oxygen level.
Moving on, NOx measurement. In chamber 1, all residual background oxygen is pumped out of the intake to completely prevent active interference with NOx measurement matrix. In chamber 2, nitrogen oxide are catalytically broken down into pure N2 and O2 element, utilizing custom rhodium electrodes. Finally, in stage 3, output generation. The resulting oxygen pump current value measures directly proportional to the total active exhaust NOx concentration. Into the next slide, key advantage. There are 4 points. High precision detects up to 5 ppm resolutions limitation. Enable Euro 6, Euro 7 compliance. Thermal stabilization maintains operation up to 900 degrees Celsius environments. Guarantee reliable inside exhaust manifold. Fast response benefit in measurement. Achieve detection times of 1000 milliseconds or less. Impact on system drive immediate real-time ECU fuel correction. Durability service life spanning up to 15,000 active hours. Greatly minimize life cycle vehicle maintenance costs. Lastly, mitigation impact. Over about 90 knots reduction achieved. Mitigation benchmark, providing live sub-second data to modern selective catalytic reduction SCR. Hardware allows targeted AdBlue dosing for maximum impact. Fuel optimization maintains strict stoichiometric boundaries to boost gas mileage. Smoke minimization target prime precursor to urban ozone, significantly cleaning regional air quality. System protection protect catalytic converter against structural rich fuel poisoning. That's all. Thank you.